Next up, we have Theo and his project, Signal Acquisition Module Prototype Development.
Hello everyone, I'm Theo and I'm one of the Horizon SPINterns. So my project is to create a signal acquisition prototype. So you might be asking, one sec. What does that actually mean? So hopefully you've all heard of Horizon's Amber constellation. This is planned to be a constellation of dedicated signal intelligence satellites. This would allow for things like economic exclusion zone monitoring, dark ship identification, counter-piracy operations with satellite phone interception, and then rescue and interdiction. The plan is that I will be making a cheaper, well, hopefully cheaper prototype using consumer hardware. And then this would be able to be tacked on to most satellites just to improve coverage. So to be able to do this, my plan is to identify signals of interest and characterize them, design and produce a prototype of the module, and then develop the test procedures needed to validate the prototype. Then I'll be creating some pretty comprehensive documentation with instructions on how to make one from scratch. And then with the time remaining at the end of the internship, I will just be expanding the capabilities of it and refining the design. So I used a lot of pretty ambiguous terms there, so I'm going to take a step back a bit and try to explain some of them now. So in the modern digital world, nearly everything is communicating with something. Your phone will be communicating with local cell towers and will be connected to Wi-Fi. For example, when I'm at uni, I can control my air fryer and my lights with my phone. So signal intelligence is basically just intercepting signals of interest, and signals of interest can be whatever information you want to find out or whatever's relevant to you. Now, I'm not saying that anyone is particularly interested in what I'm telling my air fryer and how to cook my dinner. So this is typically for more major things. So the main examples would be things like AIS from ships, satellite phones, ADS-B signals. I'll touch more on them later, but signal intelligence just improves your situational awareness. This then comes with some commercial and defense applications. Commercially, you'd be mainly looking at, say, improving the efficiency of shipping traffic in built-up areas, and then defense-wise, maybe anti-piracy. Signal intelligence can be performed using ground-based or space-based hardware, but of course for this project I'll be looking at space-based hardware. So the first main signal of interest, which I mentioned there, is AIS, or Automatic Identification System. This is used for ship-to-ship and ship-to-shore communications at around 162 megahertz. Because of the safety of life at sea legislation, all passenger ships and then any cargo ship over 300 tons has to be broadcasting an AIS signal internationally. And then these signals will include information about the ships, such as its current location, its heading, its speed, and then also where it's registered to and its vehicle registration. There's no ground stations in the ocean, so ships will form local self-organized time division multiplexing cells. These are essentially certain groups of ships within a radius limited by their horizon. And within these groups, they'll assign themselves a time slot in which to broadcast this AIS signal. This is not designed with satellites in mind, as a satellite in orbit will have a much wider field of view than the ship's horizons. This can lead to message collisions, as the satellite will be receiving messages from multiple different AIS cells at the same time, creating interference. Because of this, you'll need multiple passes per group to be able to get the full picture and understand what's really going on. And this is most impacted at built-up areas, so places like the Suez Canal, the Panama Canal, and coming into ports, which is also the areas that you'd be most interested in. Because of this, you then want as many satellites as possible to have the capabilities of detection of the signals at the very least. Then you can use things like a tip and cue system, where you maybe have a less powerful module on a satellite, can identify the location of a source of a signal, and then pass that information on to a more powerful, maybe a dedicated satellite, to be able to really lock in on the area and get a better picture of it. ADS-B, or automatic dependent surveillance broadcast, is another major signal of interest, and it's probably quite familiar to most people. This is for aircraft to aircraft and aircraft to air traffic control communication at around 1090 megahertz. There's a lot of amateur projects around ADS-B and lots of documentation on it. So I have been and I will be using this as the sort of baseline just to make sure everything's working. As if I come into any problems, then there's lots of stuff online that I can look at. It provides similar identification information as AIS, so the plane registration, its location, its heading, and its current speed. Personally, I use it when I'm in an airport just to check if there's any delays that the airline's maybe not telling us about. And then, as you can see yesterday, there's websites like Flight Radar which display the ADS-B information quite nicely. So in the screenshot on the bottom right there, you can see there was a big Embraer KC-390 in the airport yesterday for the air show. Another major signal of interest is then satellite phones at around 1620 megahertz. There's less commercial applications here with the being able to observe them, and the main applications here would be counter piracy and just intercepting voice and text data. Satellite phones typically use the Iridium network. It's the largest and most comprehensive network, as you can see from the short clip on the bottom right. The encoding of this information is pretty complex and it's very dense, so it's hard to process the data in real time. Typically, this would then be capturing it and then sending it down to ground stations, which would have more processing capabilities. Now, there's many different signals around the world. Those three are just some of the main ones. A couple of other ones of interest that I've found are VDL M2, or the VHF data link mode 2 for aircraft information transfer. There's the ATIS, or automatic transmitter identification system, for inland waterways. This would be very useful in combination with the AIS stuff to get a better picture of the traffic going through canals and major waterways. And then there's the ACARS system for aircraft communications addressing and reporting system, which is another aircraft data link. If anyone has any other signals that they know of that would be also good to look at, please let me know, as I'm continually expanding this list. So each of those signals of interest that I've listed are found at quite different frequencies. They each have their own modulation techniques and their own data formatting, some more complex than others. But due to this vast diversity of the signals, it would be pretty cumbersome to capture and decode them using traditional hardware radios. So this project is pretty dependent on SDRs, or software-defined radios. SDRs are basically radio communication systems that perform digital signal processing tasks, replacing traditional hardware components made for a specific purpose. This allows for a pretty high degree of flexibility in also a pretty small form factor, and making it pretty essential for a project like this. There's also a pretty large open source community revolving around SDRs, with a lot of software, free software for decoding the signals, and just help online. Shown here is the electromagnetic spectrum, specifically zooming in on the frequency bands used for wireless communication. All of the signals of interest so far have been around the L-band region, so about 1 to 2 gigahertz. Also of interest would be the S-band and X-band ranges, specifically for maritime radar, but this would be limited to S-band, as I will explain in a moment. So, as I said, all of these signals of interest have been within the L-band range. This is because the SDR chosen for this project, for this task, is the Lime SDR XTRX. It's a very high performance and very compact SDR running off of a LMS 7002M RF transceiver. This is capable of multiple input, multiple output operation, as it's got 2 transmit and 2 receive channels. And it's got a capability of transmitting and receiving signals up to about 3.8 gigahertz. So if I go back, that's just at the upper end of the S-band. It also, per channel, can have 100 megahertz bandwidth, which is quite handy for this situation, as if I go back again, the VDL M2 and AIS are both within 100 megahertz, so there's a chance that both of those could be captured and decoded on one channel. To run the Lime SDR, it will be connected to a Raspberry Pi 5 using a mini PCIe breakout hat. The Raspberry Pi 5 is a very low cost but suitable for this application single board computer. The module can be ran as a full desktop computer, which will help a lot with the ease of setup and the testing. And there is also room for expansion of capabilities here, as we could add a Raspberry Pi compute module to improve the processing power. So onto my actual plan. As you've seen already, I started out with about a week and a half to 2 weeks of research. This is characterizing the different signals of interest, learning about SDRs as I didn't have much prior experience. I then moved on to designing the system architecture and beginning to plan out the testing regimes. Currently, I've constructed the prototype and I'm currently working on integration of the SDR with the Raspberry Pi. Then I'll be moving on to the proper testing and the documentation, which I'm sure I'll be going back and forth as I find new signals to test and more ways of proving that it works. So here's my Gantt chart if you're interested. As you can see, as of this presentation, I'm at about halfway through the project, both in time and progress, I think. So after I researched, I moved on to completing the Great Scott Gadgets tutorials. This is using GNU Radio Companion and the Hacker F1. This is a great refresher for digital signal processing theory and also a good introduction to software-defined radios as a whole for me. As I said, this is then using GNU Radio Companion. This is a flow graph-based programming environment, specifically for SDRs. It is highly versatile with blocks for every purpose you could think of, but just not all of them work. For my uses, I'll be using it for capturing the raw radio data and then replaying it, playing it back for testing purposes through the Hacker F1. Other software that will be essential, or just the software I'll be using as a whole. Again, we've got GNU Radio Companion, which will be used for test data capture and replay. Dump VDL2 allows for decoding of the VDL-M2 transmissions in real time, which is amazing. The Iridium toolkit allows for post-processing of intercepted satellite phone transmissions. So this would be that capturing a large packet of data and then putting it into the software, and it will process it and spit out any information it can decode. SDR Angel is what I'll be using for decoding the AIS and ADS-B transmissions. It also has a great user interface, which shows in real time the locations of the boats and planes that it is detecting, and I'll show that a bit more later on. And then finally, there's Lime Suite, which is what is required to run the Lime SDR on the Raspberry Pi, as it contains all of the drivers necessary. So that's a lot of different software and would typically take a lot of setup time to get them all working nicely and working together on the hardware. Thankfully, this process is made a lot easier by using Dragon OS on the Raspberry Pi. This is a modified Ubuntu distribution, and it comes preloaded out of the box with pretty much all of the software I'll be using for this project. There's also a very active community around it, so there's lots of documentation and tutorials and help available if needed. But just as a whole, using Dragon OS has greatly reduced the time taken to get all the software up and running on the Raspberry Pi. So I looked at acquiring some sample raw data for the signals of interest, just for testing purposes and just to get a better understanding of them. I found a great resource on the SDR Angel website where it provides a long list of different signals and raw data files for them. It also comes with the file sizes of them, their bit rates, the sample rates, and the file formatting, as well as some tips and hints for how to actually demodulate them using the software. This has come in handy and will be extremely handy later on, as it provides a baseline. I have a known data set which I can process and see the results of. I've done this on one of the lab laptops, and this way I have a firm baseline of knowing what information I need the module to be able to spit out to note that it's working properly. So here you can see the result of decoding the ADS-B data on SDR Angel. On the left here is the file input. As you can see, the 1090 megahertz recording. Below it is then the FFT plot, which shows the frequency distribution over time. Then in the middle, this is the actual demodulator. Over time, that table will continually populate with aircraft IDs, their call sign, what airline it's a part of or owned by, the country of origin, and then the location and speed information. This module also then provides a pretty simplified map of the location of the planes that it is found. On the right then is a dedicated map module. This is pretty cool. It allows you to track the planes in real time. You can select one and sort of see it move through 3D space with sort of satellite view displayed below, and then also see where the plane has come from, see its path of travel. Then moving on to the AIS demodulation, it looks fairly similar again. Same again here on the left is the file input, this time at 162 megahertz, and once again then the FFT plot below it. For AIS, you need two demodulators, as there are two different AIS channels at plus and minus 25 kilohertz from the 162 megahertz center frequency. And then each of these demodulators will independently populate a table, again with important information. So as you can see, the date, the time, the country that the boat is registered to, the type of report as well, which is important for AIS, and then again the coordinates of it, its heading, and its speed. And then finally, there is the map module on the right, once again showing just a more detailed and in-depth view of the location and the path that the ship has taken. Now, I will know that the module is working to some extent if I can get these same views working on it, but with processing the data in real time, and that will be as part of my validation process. So taking a bit of a step back to look at the overall picture of the system, this is my system architecture for the prototype module. I'm anticipating this will probably change quite a bit as time goes on, as I learn more about it and figure things out, but this is how it's currently looking. So at the top, I don't think you can see my cursor, but at the top there is the Raspberry Pi 5. This is, of course, running Dragon OS, and it's connected using a mini PCIe link to the Lime SDR. Now, in real, actual scenarios, there would then be an antenna connected to this, and that antenna would then be picking up all of the signals of interest, so the AIS from the ships, the ADS-B and the VDL-M2 from the aircrafts, and then any satellite phone transmissions all over L-band. But taking a look at the testing side, because I'm looking to use raw radio recordings, I can connect a SMA cable with an appropriate attenuator and drive this with realistically a Hacker F1 running GNU Radio Companion to play back the raw data and simulate the transmission and receiving of the signals of interest in a more controlled environment. Near the end of the project, I think it'd be quite good to, as a proof of concept, to display simultaneous ADS-B and AIS decoding. I think this is more realistic to do near the coast or just near some boats, so probably down in Portsmouth or something. So I'm happy to say that after a lot of research, that the prototype itself has been assembled. I don't know if you can see it on the camera there. To get that working, I first flashed the SD card with Dragon OS using the Raspberry Pi imager, and then loaded it up onto the Raspberry Pi just to make sure that was all working okay. I then attached the M.2 hat, only to discover it was the wrong connection for the Lime SDR, as I'd gotten M.2 and mini PCIe confused. I then ordered the correct hat using mini PCIe, connected that, and so the Raspberry Pi now recognizes that there's a device connected. It knows that there's meant to be something there, but the drivers are not fully compiling. There's an issue going on there, and that's what I'm currently working on. I know that it acknowledges that there's a device there. It just won't enumerate it as a device. It won't give it an ID to be able to communicate with it. So here are the pictures of it, if you couldn't see it in the camera. This is what it's looking like so far, with all of the components put together. At the top, you can see the top level, then the blue board is the Lime SDR XTRX. This is then connected into the mini PCIe hat. And then that is then connected to the hat is then the blackboard, sort of in the middle there. And then at the very bottom, at the base of it, you have the Raspberry Pi itself, which is encased in a nice little red case. You can see there's two small cables coming out of the Lime SDR, but due to the very, very small form factor of the Lime SDR, it does not have room to have full SMA connectors. So these cables are UFL to SMA connectors, which just allow me to connect better sized antennas and cables. So for the future, what is left to do? The current hurdle, as I said, is getting the Lime SDR to actually communicate with the Raspberry Pi. I've found some pretty promising threads, so hopefully I'll be able to work through those tomorrow and get it actually communicating. This is going to be sort of the major hurdle for the whole project. If I can get them communicating, then it's just a matter of finding the software, finding the right open source decoders to be able to receive and process any of the signals of interest. I will then hopefully in the next week be running up a lot of my documentation, mainly for the construction and the setup phases of how to get the module assembled. Hopefully doing this sooner rather than later, just while it's all in my head, but I've hopefully kept pretty good notes, so that shouldn't take too long. Finally, I'll be moving on to the actual full testing for the module. As I said, I've got the sample data for AIS and ADSB. I'm still looking for sample data for the satellite phones, but I'm not sure that is something that's freely available. So there's a chance that will have to be done by a real world test only. So then, yes, after using the sample data to test it, then I'll be moving on to the real world tests, proving that it can receive the information and decode it in real time for most of the signals of interest. And then it will be a matter of just continually improving the capabilities of the module, expanding the list of signals of interest, and refining the design and getting it all working. So that is the end of the presentation. I've ran through that a bit quicker than I thought I would, but thank you all so much for listening.
Lastly, we have Hani and his project, Satellite Signal Acquisition Algorithm Development.
I'm Hani, I'm the other Horizon intern, and my project is Signal Acquisition Algorithm. It sounds really similar to Theo's. That's because two of the three words are the same. I'm the algorithm side, he's prototype. They're two different projects. He's more on the hardware side of creating the hardware to pick up the signals, and I'm more on the software side of simulating signals and then being able to pick those up, both on PC and not like any hardware involvement. But I'll explain more about that in a moment. So there's a lengthy job description that details quite a few different things to consider when carrying out this project. So it talks about familiarizing myself with the software, setting up the test bed, and identifying things that are necessary. That's all pretty similar to what Theo was doing. For the first week or two, we were both researching things, sharing some notes sometimes. But it also talks about being able to simulate signals of interest as well as create the software to pick that up and decode it. But I summarized it here in a sentence. Use of software-defined radio hardware and software tools for signal generation and acquisition. So essentially, it's just signal created in PC, sent to a hack RF, which is able to be picked up at another hack RF, which sends it to a PC that it's connected to, which will be able to process that data. So essentially, there's two parts to my project. There's the signal generation, and then there's the signal acquisition. So I'm planning to put both of those into one single piece of software, but essentially have like two modes that you can use depending on what your intention is. In terms of the tools that I used, similar to Theo, I used HackRF and GNU Radio. So the HackRF is a software-defined radio, and you've just heard about that, but I'll explain really quickly. It's essentially a radio transmitter and receiver, a transceiver, which can send radio signals and receive them. And unlike a traditional radio, it uses software rather than electronic components to process the signals. And importantly, it's compatible with GNU Radio. GNU Radio is a software development toolkit which can help with signal processing. It's really convenient because it provides simple blocks that can process the signals that come in, and means that like limited knowledge in terms of electronics components is needed. So it's really useful for software-defined radios. There's an example of a flow graph in the top right there. But yeah, those are the two main things I did. In terms of getting started with the project, the first thing I had to do was obviously familiarize myself with the task, but also plan. So there's my Gantt chart. I know Catherine really likes these. She let me know that I should probably make one, and that was a very good idea because it has allowed me to organize my time a lot more than I would have done. So there we go. We've started on the project. So in terms of HackRF and GNU Radio familiarization, I have dealt with the GNU Radio tutorial for the first few like steps of creating blocks, understanding generally how the software works, how I can process simple signals, all the way to more complex techniques in the software. I've also done Great Scott Gadgets, which there are 10 or 11 hour-long videos on YouTube, which went through like tutorials of how to use the HackRF, which I also watched. After that, I had a good base to start the project. So I started with AIS, as that was the main thing that was detailed in the job description, was to process AIS signals. So I started with the AIS handbook, which was from Big Ocean Data, which is a big vessel company essentially, and they just gave a small overview of what AIS is and how it works. I also went with the US Coast Guard for some of the information regarding the messages and also general information concerning AIS. I made some notes on those in the team files area. I also used MATLAB's guide, except it was explaining how to implement it in MATLAB, but some of the information was still useful in terms of how the packets were organized. There's a lot of information online about like examples of different AIS messages that you can see. So all of those were really useful to understanding how AIS packets were crafted essentially. And then here's my old friend ITU-RM1371-5. This is a piece of a recommendation, a guide on that standardizes AIS that I had to look through quite a lot during this project. It also points to another paper, the ISO's 13239 2002, which standardizes HDLC messages in general. So those were very useful in understanding how the messages are made and transmitted. In terms of looking out to see other people who've done somewhat similar things, there were a scattering of random GitHub repos that had certain vaguely similar projects, but most of them were only in terms of decoding and not simulating a signal. So they were useful in terms of understanding how implementations might be created, but not in terms of being able to just copy and paste, which was annoying, but also allowed me to actually do a project. There was also Fun with Electronics, which had an example of how GNU Radio was used to process, which was really helpful with creating my flow graphs that would be able to take the output of my Python and spit out a signal from the HackRF, but that's something I'll talk about a bit later. And there were more GitHub repos essentially. In terms of what AIS was that I discovered from all my research, it's essentially a way for ships to communicate. They can send an I am here message to each other and can avoid collisions amongst other possible message types you'll see in a second. So this is an example of an AIS message that is sent specifically between equipment on the it's specifically sent between equipment on the ship itself. So you've got the starting message type AIVDM. There's also AIVDO. AIVDM shows that the message was received outside. There's the number of sentences. So theoretically, you could split an AIS signal up into pieces and send it one piece at a time. Essentially, that's what the next few fields are for. The main thing that I'm dealing with is the encoded AIS data, and that's 6-bit ASCII encoded AIS data that's done in a very specific way that I'll also explain in a second. But essentially, that's the main thing that I had to deal with transmitting, because this packet I'm showing you now is not the one that is actually used for transmitting between ships. It's the one that's used for inter-equipment communication, essentially. So this is more the type of packet that is used between ships. So based on the ISO's HDLC specification, you have the data in the middle, which is encoded in a very specific way. You've got ASCII 6 rather than UTF-8, which is the standard ASCII encoding. You've also got the training sequence and start flag, and the frame check sequence, and the end flag and buffer. So those are just essentially extra additions to allow the computers to understand what's being said. Again, these two documents, very helpful. So these are I just wanted to show how many message types there were. There's so many AIS message types, and each of them has like a different sort of field, like number of fields and type of fields and things like that all have to be considered. So with that, I had started with creating the AIS packets that could be sent in order to create the simulation testbed. And very quickly off the bat, I found a very convenient library that someone had already made, HiAIS, which really made my life simpler because it meant I didn't have to deal with every single message type. So essentially, I just managed to import this, and once I took a while understanding how it worked, I could successfully encode AIS data quite easily by just inputting the fields and being able to use functions that it provides. Again, this paper was really helpful with being able to make sure that everything was up to scratch and wasn't just like wrong. That paper appears a lot in my project so far because that's essentially the thing that I depended on to understand the whole topic. But yeah, once I had generated an AIS, which depended on other functions I'd written as well, that was really convenient to be able to just use. And I made sure to write my code in a way that with my future plans, the whole thing will be easily integratable into like another part of the project that I'll be making later. What you'll see on the right there is a dictionary that I'm using to essentially store all the information, and that's essentially me, like I just said, making the code accessible to my future self who's going to be dealing more with the inputs. But yeah, I'll talk more about that in a bit. I mean, if you're particularly astute, you might have noticed that I'm creating the checksum myself, and that is a whole thing that I'm going to talk about in a second. So you might think that a checksum would be easily discoverable in a pre-made module, and you'd be right. I found CRC mod amidst other less Python-oriented libraries, but I could not get it to work for the life of me. It did not copy. It did not like check things properly. It didn't give a proper output. It didn't like create a proper checksum essentially. And well, by the way, the way I know this is again through ITU-R M1371-5, which was like there with me every step of the way, and it wasn't essentially creating a checksum that was valid according to that. So this is specifically what's described, but I could not understand most of what was written here, even through like multiple readings. So what I later discovered was that there was in fact an annex that explained a very specific implementation. So with that, I was able to make some simple code that used modulo 2 division, as well as other techniques that were explained in a handbook, and basically made some code to be able to just plug into things. And I tested that thoroughly, and it seems to work. So I was now able to create AIS signals and save them to a file. So in terms of transmitting and receiving AIS signals, so this is more the middle part of the graph I create, a diagram I showed you at the beginning. This was more GNU radio. So I made a flow graph for transmitting and one for receiving. The one you're seeing right now is the one that made my life easier because I didn't have to deal with HackRFs directly. So essentially at the top there, you can see the first line is it's getting the information from a file source, and it modulates it and sends it to essentially another line that can put in some noise and pretend that it's like a channel, and then the third line just receives it and demodulates and splits it up into the right number of bytes and so on. But essentially this flow graph allowed me to circumvent the need for HackRFs with direct testing, which has been both a blessing and a curse. It's been a blessing in that it's made my life so much easier with being able to test my Python code, but also a curse in that I now need to actually deal with HackRFs to be able to say that I have sent and received signals. So this flow graph has just been a convenience so far, basically. With GMSK modulation, I was very thankful for that block, because otherwise I would have actually had to deal with how GMSK specifically works and understand it a bit more than I do. And that, again, made my life easier. I do understand it, but not to the extent that I could recreate that block yet. So on the other side, with parsing AIS packets, I essentially just did the same thing on the other side with PyAIS, and was able to just get the AIS message in bytes, find the start flag, and cut out the data from right after the start flag, check the checksum, and be able to read the information and print it out. My hopes are that later in the project I'll be able to do that with several different data types, and then be able to make that a more convenient thing to do without having to run many different programs. But again, that's something I'll talk about later. So essentially all these building blocks of sending and receiving are put together. So I've got test signal generator script, which is able to talk to GNU radio, which sends it to a HackRF, which sends it to another HackRF, which will send it back to GNU radio flow graph, this time on the receive end, and that'll send it to the message parser. And of course, there's some code just to like support it on the checksums, and as well as like providing random small functions that are necessary. But that's essentially the main structure of my project so far. What I did, as I just described, was replace all of that process with a single flow graph just for testing. But what was the case is something that I'm going to implement probably next week. So in terms of the organization of my files and how they currently work, I've got my signal testbed file, and in that I have Python scripts that are going to be relevant to all the signal types outside. So I've got message info, which defines the dictionaries that are going to be carrying the data into the signal generator being there, and I hope that all the functions for each signal generation will be able to be in that one module that will be able to be used by another script. And I also have the message parser, which is also there, and that's able to do the same but in reverse. I've decided that each signal type should be stored in a specific folder, just for ease of being able to understand where everything is and how it works. I've left out the Python scripts that are generated when you run GNU Radio Companion, but essentially it's the same thing as what you can see at the bottom, but .py instead of .grc, and essentially they just process and modulate the signal before being able to communicate with the HackRF. crc.py is also the checksum program, essentially. You've got input and output data, which is stored in .bin files. So as the future of the project, you can see there on the right, there's a picture of society if my project ever gets completed. So I'm going to test what I've done so far with HackRFs, because so far I've been using that channel simulator. Hopefully it should just be like a quick plug-in HackRFs, it works. If it doesn't, then I'll have to get more into the hardware side of understanding what is going wrong with HackRFs rather than with my programming. Add more signals. So currently I've got my eye on ADSB, which, like Theo has mentioned, is essentially the same thing but for planes rather than ships. Obviously the whole packet structure and things like that are going to be different, but in terms of the purpose and the use of the signal, that's essentially it. VDES is essentially a more advanced AIS signal, which is two-way, so that might introduce some complications into my into my architecture so far, but that's something I'll consider when I get to it, essentially, because I haven't researched these signal types enough. There are other ones that are mentioned on the job description, and I will check those out in due course as well. I aim to create an overarching script, because right now what you have to do is you have to create a signal with test signal generator that creates the output data, and then you run the GNU Radio script, and then that sends it out, and then you'll have to do the same on the other side. I'd like to create one script where it's very easy to just say what you want to send out and be able to send that out. It'd also be nice if I have the time to add a GUI. So I was thinking of using tkinter. That's a library for Python GUIs that I've used in other projects, and that essentially would just make the whole thing easier to use. Also, I'd like to finish my documentation. I've started it, and it explains what each part of the project does, and as well as how to use it. But again, that's something that will constantly evolve as the project itself does. In terms of what I've learned so far, I have learned a lot about signal standards, perhaps more than I wanted to. So again, ITU-R M1371-5. It's something that I have become very acquainted with. I've learned a lot more about how to organize a software project. So I've actually organized my project far better than I have in my own personal projects. And that's something I also had to research. So in my own personal project, I just have lines of pure messy garbage just written in unorganized layers. Right now, I've actually organized my project somewhat understandably. So that's something I'd like to improve as well, and I have done so far. I've also learned how to bully the code into working. So essentially, debugging the code is something that I've already knew how to do somewhat, but I did not. Especially with the checksums, I found a lot of issues, and that's just something I had to cross-reference with the book that essentially explained the specifications. So it's just something else that I had to consider when debugging, is the information that is out there and how to consider that when considering why there are issues in my code. Also, the Gantt chart, that's a new thing for me. So just being able to block time out was very helpful. I'll be using Gantt charts in my own personal projects from now on, I think, because it was just really helpful to be able to see what I had to do by when. So yeah, other than that, I have explained my project and how it works generally and what I hope to do. So thank you for listening.
Thank you to James, Harvey, Theo and Hani for sharing their presentations with us.